layout. Very time consuming. Here, the design needs to fit together nicely, and we need to build a library of standard cells. And in standard cell design methodology, so here we have some standards in order to design the layouts. Usually, the VDD and the ground should be in standard height. Adjacent gates should satisfy design rules. The NMOS should always be at bottom and PMOS should always be at top. Here, the all gates include well and substrate contacts. So whenever you are constructing a layout, the construction of this layout is very time consuming. And here, whatever the gates that we will going to design has to be fit properly. And also, we need to build a library of standard cells. So this standard cell design has some methodology and it has to follow certain rules. Usually, whenever you are constructing this VDD and ground, these two are power supplies, should be in standard height, and whatever the adjacent gates should satisfy the design rules. Always the NMOS should be at bottom and PMOS should be at top. Here, all gates which include well as well as substrate contacts. Here I am taking a simple example that is nothing but an inverter. So here you can see this is nothing but a layout of an inverter. So before constructing this layout, we will going to see the schematic of an inverter. So usually the schematic of an inverter consists of PMOS transistor and also NMOS transistor. So here this is nothing but input A, and here this is nothing but output Y, and this is nothing but ground, and this is nothing but VDD. So this is a simple schematic diagram of an inverter. This is PMOS transistor and this is an NMOS transistor. So here you can see that this is nothing but metal. So this is nothing but a VDD. So this is nothing but whenever a gate crosses diffusion, then there will be a formation of transistor. So here we are having only one input. We can call it as A. So this is nothing but A, and this is nothing but P diffusion. When gate crosses the P diffusion, PMOS transistor will be formed. When gate crosses the N diffusion, the NMOS transistor will be formed. So this is nothing but metal. The source of PMOS transistor should be connected to VDD, and similarly, the source of NMOS transistor should be connected to ground. And the drains of both PMOS and NMOS transistor can be given to output Y. And this black color one, which indicates the contacts. So these are nothing but contacts. Similarly, here there will be a formation of well and substrate regions. So at the NMOS there will be a formation of substrate T, and at the PMOS there will be a formation of well region. So here I am taking a simple example that is nothing but a 3-input NAND gate. So if you consider 3-input NAND gate, as we are having 3 inputs which can be represented as A, B, C, and also at the top we will be having VDD. At the bottom we will be having ground. So this is nothing but a P diffusion and this is nothing but N diffusion. So usually the horizontal N diffusion and P diffusion steps. So here we are having horizontal P diffusion step, and here also we are having horizontal N diffusion step and vertical polysilicon gate. These are nothing but gates as well. It is a K-input NAND gate. So we will be having 3 inputs A, B, C, and metal one. This is nothing but metal one rail at the top, that we can call it as VDD, and the metal one ground at the bottom. Here, in order to calculate the horizontal width and vertical height, so here the horizontal width is 32 lambda and vertical height is 40 lambda. So in order to calculate horizontal width, so we have formula that is space. First thing is we need to consider the diffusion having more number of contacts. So here if you consider P diffusion and N diffusion, here the P diffusion is having more number of contacts. So the formula is spacing plus 1 into 8 lambda. So in order to calculate horizontal width 32 lambda, the first step is we need to consider the diffusion having more number of contacts. Here this is P diffusion and this is an N diffusion. So P diffusion has more number of contacts than N diffusion. So the formula is spacings plus 1 into 8 lambda. So here from ear to ear, from one contact to this contact, one spacing. From this contact to this contact, second spacing. And from this contact to this contact, third spacing. So how many spacings are there? 3 spacings plus 1 into 8 lambda. So the horizontal width, 8 4s are 32 lambda. Similarly, in order to calculate the vertical height, the first thing is we need to consider the metal connection with contact, but it is not supposed to be in similar direction. If both are in similar direction, then you have to consider only one. So metal connection with contact plus 1 into 8 lambda. So you will be getting 40 lambda as vertical height. So next we will going to see the stick diagrams. So stick diagrams are mainly helpful in order to draw the layouts very quickly. So here it need not to be scale, and here we can draw the stick diagrams with the using of different colors. So here you can see that the metal one has to be drawn with the help of blue color. So the metal one should always be in blue color, and the polysilicon should always be in red color, and the end diffusion it always be at the bottom, should be in green color, and Q diffusion should be in yellow color, and this cross marks which indicates the contact should be in black color. So this is the stick diagram of an inverter, and this is the stick diagram of a 3-input NAND gate. So at the top we will be having VDD, at the bottom we will be having ground. So it is an inverter. It has only one silicon gate, that is input A. And whenever the gate process diffusion, there will be a formation of P transistor. So the yellow color which indicates the P diffusion, this red one is a gate. When gate process the P diffusion, there will be a formation of P transistor. Here also green color indicates the N diffusion. When gate process the N diffusion, there will be a formation of N transistor. So this is one contact source, this is gate, and this is drain. Here also source, gate, and drain. The source of PMOS should be connected to VDD, and the source of NMOS should be connected to ground. Similarly, the drains of both transistors can be given as output Y. So this is the stick diagram of 3-input CMOS NAND gate. So this is nothing but VDD. Here also will be having ground. So this is nothing but yellow color, which one indicates P diffusion, and green color indicates N diffusion. So this is a 3-input CMOS NAND gate. So here we are having 3 gates. So next we're going to discuss about the wiring track. So wiring track is nothing but how much space required for a wire. For example, if it is 4 lambda width, then the spacings will also be 4 lambda from the neighbor, totally 8 lambda pitch. Here the transistor also consume one wiring track. So here we are making use of 2 metals. So metal 1 and metal 2. So the width of the metal 1 is 4 lambda. Even the spacing is also of 4 lambda, total of 8 lambda. So here you can see this. So next is well spacing. So well must surround transistor by 6 lambda, and it also implies 12 lambda between opposite transistor flavors. If both are opposite transistor flavors, then it can implement with a 12 lambda, and it can leave room for one wire track. Here the spacing you can see between 2 opposite transistors, there will be a 12. Here also you can see it should be of 12 lambda.